If any of you have looked into Brightspace, you saw that the last session we had wasn't recorded properly. I got the video, but there was no sound. And the only thing I can think of as causing that is the IT coming in and doing things. And I didn't start from scratch again. I probably should have gone all the way back and just reinitiated Zoom and started over again. But I didn't. So part one is missing. We have to go back to a previous video to see the material that was covered last week. Hopefully, we'll get all of part two recorded, and that way it'll look familiar to you when you go back and take a look at it. First thing I want to do is, before we pick up exactly where we left, questions? Any problems? No? Okay. I want to go back and review the 4 quantum numbers, because they're going to come back over and over again in this chapter. And if we start off with, see if this will write. What was the first one? Principal quantum number. And this one is actually the same number that Niels Bohr, when they came up, not Max Planck, Niels Bohr. When Niels Bohr came up with his energy level, his orbital model, he used numbers from 1 through whatever. And they were retained in the quantum mechanical model of the atom. Model. And what the principal quantum number is expressing in those wave equations, the Schrodinger's wave equations, is approximate energy and size of the orbital, or of the everything at that energy level. Next one. Oops. Oh, and these numbers can be 1, 2, 3, up to whatever we need. Then there's L, which is the angular momentum. Quantum number. And this one is an expression of the shape of the orbital. Okay. And these can be anywhere from 0 up through n-1. At any one of these levels, we can apply and branch that level out into a number of L's. This is called a shell, and this is called a subshell. There we go. And then we go to M sub L, which is the magnetic quantum number. Quantum number. And this is orientation in 3-dimensional space. And these values can go from L, minus L, up to 0 to plus L in whole number increments. So if we had an angular momentum here of 3, it could go -3, -2, -1, 0, +1, +2, +3. And this is called the orbital. Let's see, you just dinged in. Kaylee. All right, and the last one is the easy one. M sub s equals the spin quantum number. And this can be either plus 1/2 or minus 1/2. I can do better than that. There we go. And that's exactly what it says. It represents either spinning one way or spinning the opposite direction for the electron. Okay. So when we write out the electronic configuration of an atom, we keep these numbers as the first number, and then we can have multiples of these sometimes, but these are given letters just to avoid confusion. The zeros are the S's, P's for 1, D's for 2, and F's for 3. So if we did something really simple like hydrogen, right? We know hydrogen has 1 proton, and when it's neutral, it has 1 electron. So we start at the lowest energy level with 1 electron. That's hydrogen, 1s1. If we went to helium, right, it has 2 protons and 2 electrons. It would be 1s2 because they can be in the same orbital. That means that these 2 electrons have to have opposite spins. And we represent those, if we, sometimes we do this underneath to show that 1 electron that way and 1 electron that way, opposite spins. This one would only have 1, like that. Okay, we'll do some more complicated ones in a few minutes. So that's a review of quantum numbers. Now let's skip over that other stuff and move to where we left off. I was about to talk about, we covered the Pauli exclusion principle and polyatomic atoms, polyelectronic atoms, the penetration effect. Okay. So let's define what we mean by the penetration effect. And this concept is, I wouldn't say derived from, but it's dependent upon, in some respects, to the fact that as you add more electrons and more orbitals, they start to interact. And when they do that, they shift the actual energy levels of the orbitals themselves. Whereas the principal quantum number gives us an idea of the energy levels, but within that range, the shells are that within that range. Then within that range, you have orbitals, and they can vary because of the interactions of multiple electrons. And so one of the effects there is this penetration effect. So when we say an electron penetrates to the nucleus more, what we mean by that is that the expression, the probability of finding the electron for that particular orbital moves closer to the nucleus. Now, there may be a range, a spread of possible locations for that electron, and right, this is all probability based. So within that range, we could find the electron anywhere in there, right? And that's largely due to the Heisenberg uncertainty principle. But we can calculate what's expected for the locations of the electrons in a probable scenario. And then we can draw them out on a graph. And that will give us an idea of where we can expect to find that electron. And remember, one example where we had the 1s, the 2s, and the 3s orbitals, and they were all spherical, but the 1s had no nodes. The 2s had one node, where the probability drops to 0 at a certain distance from the electron, from the nucleus. And then the 3s had two nodes, where the probability drops to 0. Well, we can put that in a graph where we have the probability of finding the electron on the y-axis. I think I need to ditch that one. So this would be the probability of finding the electron, and this would be the distance from the nucleus. Okay? So at the nucleus, none of the orbitals are going to have a probability, right? You're not going to find an electron at the nucleus. But for the and we're using the principal quantum number 2, or the shell 2, and let's say an example there would be, say, say boron. Boron would have 5. Okay? So we put them in order like this, like 1s, and 2 electrons there. We got 3 left over. We can go to 2s. Right? We got 2. Now we need one more. We go to the 2p, gradually increase the energy here. So we have an electron in the p orbital for 2 and 2 in the s orbital. When we draw out the probabilities, remember the s is going to have a node, and it will have a probability like this, right down to 0, and then its probability will go up at this distance. So we're more likely to find the electron out here, but there's still a probability that you'll find it this close to the nucleus. Okay? The probability for the p orbital is just a single hump, right? And it goes about like this. Something like that. Well, actually, it coincides with this one over here. I didn't draw it quite right. Let's see if I can do that again. Like that. Now, if we say which electron has the higher energy, the temptation is to say, well, if this one is the 2s and this one's the 2p, then the 2s does. But the 2s penetrates closer to the nucleus than the p does. So that's why we give the 2s a lower energy. So it'd be to the left. This has a lower energy than the p because of that penetration effect. If we look at the 3s orbital, then again it's spherical, but it has 2 nodes. So it would look more like that picture. Yeah. They did a better job of drawing it than I could. See, the probability goes to 0 at certain distances from the nucleus. And those closer humps are called the penetrators, I guess. Well, I don't think that's a proper term, but that's what I'd call them. They penetrate to the nucleus. Now, if we look at the 3s, like we did with the 2s and 2p, now we have the 3s, the 3p, and the 3d. Okay. Now, why do we have that? Well, if we have 3 equals n, what are the possible L's? The L's could be 0, 1, or 2. Right? So this is S, P, and D. So now we have access to D subshells. D subshells. So that's why we've drawn a 3s, a 3p, and a 3d here. The 3d has a single hump as far as distance from the nucleus and probability of finding the electron. The p has two humps with one node. So it has some penetration toward the nucleus, which puts it at a lower energy level than the D. And the 3s has two humps with a penetration closer to the nucleus than either the 3p or the 3d. So that's why we are able to assign energies to the 3s lower than the 3p or the 3d. Now, what we didn't draw in here was the 4s. The 4s is going to have three nodes, and it's going to penetrate actually closer to the nucleus than the 3d. So if we drew in our 4s here, there's the 3d right here, right? If we drew the 4s, it's going to have its major hump out here, and then it's going to have three more, probably in here somewhere, and down in here somewhere, at a lower energy than the 3d. So, and remember that because that's going to influence how we construct the periodic table. You'll see that again in just a few minutes. All right, so the periodic table, where did it come from? Well, it took several decades to get a workable model, a workable periodic table. And the story is long and interesting, but these are the highlights. Right? So one of the first chemists who proposed an arrangement of elements that were similar in nature. Remember, at these times, 18th and 19th century, early 19th century, actually until the beginning of the 20th century, the only thing that chemists could describe about compounds and elements was their mass. They had no idea about the structure of the atom, right? They couldn't associate any type of trend that we now do for the periodic table. They couldn't associate those trends with the elements because all they knew was mass and certain other physical and chemical characteristics. So that's what's so amazing about the periodic table, that they were able to build it without knowing that information. Later, we superimposed the structure of the atom on the periodic table, and it fits very nicely. But first, one of the first chemists who recognized a trend was Johann Dobereiner. He was German, obviously. And he had several groups of elements, three in each group, that he called triads. And he noticed that they had similar chemical and physical properties. Well, actually, chemical properties primarily. Chlorine, bromine, and iodine we recognize now as halogens, and they behave similarly in a chemical reaction. They don't have the same states, right? At 1 atmosphere pressure and room temperature, chlorine's a gas, bromine's a liquid, and iodine's a solid. So they're not related that way. But that's as far as he took it. He just recognized these triads. Then sometime after that, several decades actually, we get Julius Lothar Meyer, who was also a German. And he proposed a table of elements that they knew at the time and tried to arrange them in such a way that they related to one another. And very close to that, actually almost simultaneously, Dmitry Mendeleev, who was Russian, put together his periodic table. And his periodic table, the first one he published was the periods were up and down, and the groups were left to right. So these groups would have been turned 90 degrees. The second time he published, he rotated them into our familiar arrangement. But he grouped the elements by their physical characteristics, their chemical properties, and how they reacted primarily how they behaved in terms of their oxides. Because most of the metals on the periodic table, especially, are found in the crust of the earth as oxides. So that was a common way of expressing metal mass. Anyway, he arranged the elements in his periodic table, but he went a step further. What he noticed was that when he tried to group some elements, he took them by their weights, the weights that they knew at the time, and he arranged them in order by their masses, and he tried to group them. So if if we come along here like this, and we have these in that group, and we have these in this, I'm just hypothetical. So we've got an element here, we've got an element here, here, and here. Those lighter elements, they're all known. So then he comes along and he finds that this next element, which is more massive, all right, it fits in that group. It's just like this element, right? But he says the next one that we know in the next highest mass doesn't fit that group, right? It doesn't have the right characteristics. He said, it's more like this one over here. So he put it in that group. And he said, this one and this one aren't found yet. But when we do, they will have this mass, and they will have these characteristics. Right? He lined it out and said, that's what we can expect, because he knew what their group was like. So he left those places empty. And sure enough, sooner or later, those elements were found, characterized, and they fit very closely to what he had predicted. So that's why Mendeleev gets the lion's share of the credit for the periodic table, because he used it to predict the existence of as yet undiscovered elements. Okay. So now the general layout of the periodic table. And let's see, I need another marker. The general layout of the periodic table goes something like this. All right, we have hydrogen up here, and we have helium up here. So this would be period 1, this would be 2, and this would be 3, and then we get to 4 and on down. All right, so the layout of the table is such that these are the groups. They have similar characteristics, and you've been exposed to a number of them already. Right? Did we do the extra credit yet on the periodic table? Okay, good. Okay, I'll be sure I get that in the mix. So you know that this first group is alkaline metals. Second group is alkaline earths. These are the transition metals or transition elements. These are the noble gases. The next group over are the halogens. And then the next group, starting with oxygen, are the chalcogens. Yep. And then the nitrogen group is called the pnictogens. Start with a P, but the P is silent. And then you have carbon and boron and their groups. Okay. Now, the way we numbered them when I was a student was this would be 1, 2, 3, 4, 5, 6, 7, 8 Roman numerals. And these would be the A groups. Roman numeral 1A, 2A, 3A, all to 8A. And then this would be the B group. And we did that because the A group was very well behaved. The elements tended toward an octet in their outer orbitals. When you get into these right here, they tend to get messy. The reason for that is these are all d orbitals. You're filling d orbitals. I'll come back to that in a minute. I left out the lanthanides and the actinides. We'll come back to those too. Now, I don't think we've mentioned it so far, but when we count all of these together with all of these, Those are called representative elements. So if you ever hear the term or read the term representative, they're talking about these and those. Because these are, we're filling s orbitals here, we're filling p orbitals here, we're filling d orbitals here, and then the lanthanides and the actinides, we're filling f orbitals. Those are the ones that are, and what we mean by filling is, as we go from one atomic number to the next highest one, we add an electron, and that electron goes into a d orbital. Let's see. All right. So you might remember that if you start just under boron, go down like that, and one element at a time, you stair step it like this. These are nonmetals. These are all metals. So most of the periodic table is metals. And that includes the lanthanides and the actinides. And they share some basic characteristics. Metals, for the most part, are all solids at room temperature and pressure, except for mercury. It's a liquid. The rest of them are solids. Now, some of them have very low melting points, like gallium, right? You can take solid gallium, put it in your hand, and it'll melt. But the nonmetals run the full gamut. Some are gases, some are liquids, and some are solids. Then there's this group right along the boundary of the metals and nonmetals called the metalloids. And they behave, sometimes they behave as nonmetals in some environments and metals in other environments. So, and the ones that are considered metalloids vary depending on the author. Okay. All right. So as we're trying to build our elements, one proton and one electron, right? We're neutral so far. Neutral, as we're building from left to right, top to bottom, the atomic number gets bigger as we go from left to right and then top to bottom. And the number of electrons add at the same rate because we're still neutral. So positive and negative have to balance. Let's see, I was going to say something else. Just flew right out of my head. So I can back up and catch it. Oh, so these are groups up and down, and these are periods across. Now the groups are fairly intuitive, right? They all have similar properties. The periods take a little explaining. And the way I explain that is to go to physics. I've asked you the question before, right? Anybody here have physics? No. Physical science, maybe? No. Okay. Well, there's a type of motion in physics called periodic motion. You can have linear motion, right? So if you set something in motion according to Newton, if no other forces act on it, it's going to continue in a straight line with that velocity forever, unless something acts on it. So if we throw a satellite into orbit, gravity's acting on it. So it has the same speed, but a different velocity because it's changing as it goes around. But that's linear motion or circular motion. Periodic motion is the object is moving, but it's moving in such a way that it goes to one point and then it comes back to the start and does it again. Think of a pendulum. That's a good example of periodic motion. So we call these periods because as we're adding protons and electrons, as we go bigger and bigger and bigger and bigger, we get to the point out here where, wait a minute, this element looks like that group. So if we put it out here, we got to start a whole new group that looks like that one we already got. So we just swing around, start a new period. That's why it's called a period, because we get to the end, start over again. Okay, the Aufbau principle. Let's see, we've done the Pauli exclusion. There you go. There it is. I have to throw those out. Trying to get some more life out of them by storing them upside down. We've done the Pauli exclusion. Remember what that said. No electron in an atom can have exactly the same 4 quantum numbers. All the electrons in the atom are unique in that respect. If they have the same first 3 quantum numbers, then the last one, the spin number, has to be different. Okay, that's the Pauli exclusion principle. The Aufbau principle excuse me, says that as we're building the atoms, the next electron, when you put a new proton in there and an electron comes with it, the next electron has to go in the next available lowest orbital. Okay, you can't go along and say, well, I want this electron to be out here at a higher energy. Doesn't work that way. You put it at the next available lowest energy state as we build. That's what Aufbau means. It's a German word, and I don't know German. Somebody told me one time, Aufbau means do it this way. I don't know. So that's why, and we're going to show you the energy order of orbitals. Oxygen in this, we did 1s, 2s, 2p, that's order of energy. And that's how we add the electrons. And I'm going to show you how to, actually 2 different ways, how to set that up so you get them in the right energy order. And then Hund's rule takes a little explaining. Recall when we have, say, n equals 2. What can L be? L can be 0, 1, or 2. 0 or 1, right? N minus 1. So this is S and this is P. All right. How about M sub L? Well, M sub L is minus L to plus L. So for 0, there's only one choice, right? You can have one of these, right? You can have a 0 here. But for the 1, you can have a minus 1, a 0, or a plus 1 for the P. Okay? So shell, subshell, orbital. You can have 3 orbitals for every P. So that's, I represent those orbitals with the line so that I can put electrons into them. As you add electrons to p orbitals, or d orbitals or f orbitals, which have multiple levels here, Hund says each additional electron must be unpaired until you exceed the number that can be separated. So with 3, they can all be separated. But now if I go to 4 electrons, now you can start pairing them up. And that's largely due to the repulsive effect. So Hund was implying from this rule that the electrons tend to go in these separate orbitals because they repel one another. And you can only put one in there because there's no other place for it to go. That's the way I look at it. That's Hund's rule. All right. So for oxygen, right, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons. Is that right? Yeah. 8 for oxygen. 8 protons, 8 electrons. So we use the alpha-val principle. Two of them can go in 1s. 2s is the next highest energy. You can put two more in there. 2p is the next one. Now you've got what? You got 4 from 8. You got 4 more left. So you can go 1, 2, 3, and then come back and pair up. So that would be the lowest energy state for oxygen at standard temperature and pressure. Now, what do we mean by valence electrons? Well, if we go back to our oxygen, okay, yeah, 8. Valence electrons are those that are available for chemical reaction. Non-valence electrons do not react. Right? These valence electrons are in the outermost shell. And when I say that, I mean that literally, because the shell is the principal quantum number. Principal quantum number tells you your valence electrons. So the highest number here is 2. That means these 6 are valence electrons. Okay? And elements in the same group, especially for the representative elements, they're very well behaved, electronically speaking, unlike the transition metals that tend to get wonky sometimes. Every element in this group has the same number of valence electrons. That's why they have similar chemical behaviors, because they have the same number of electrons available for reaction. Come on. There we go. Okay, I showed you this earlier, kind of a teaser, I guess. When we start filling by the alpha-val principle, you can go step from left to right, top to bottom. And as you go, you're adding another proton, another electron to the configuration. You can only put 2 electrons in the s orbital. That's why these two are grouped together. These are all 1s, 2s. Okay? These are all P1, P2, P3, P4, P5, P6. All of them. That's why they behave the way they do. Similarly, the d orbitals, how many can they have? Well, let's look at it this way. Okay, remember the p orbitals can have 3, right? And we did oxygen like this, like this, like this, like that. Suppose we have we have to go to the third level to get Ds. So if we have a 3D, we have 1. D would be 0, 1, 2, right? Would be L equals 2. So that would be -2, -1, 0, +1, +2. That's 5. So we can have 5 orbitals at the D level. There we go. Okay, so how many electrons can we put in there? Total. 5 times 2 is 10, right? 10 electrons. So that means 10 electrons equates to 10 protons. We can build, with just this one orbital, we can build 10 elements. Okay? So if we're in the transition element arena, we're filling d orbitals. That means as long as we're filling those d orbitals, we're in that purple region. And count how many squares there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 squares there. And by the time we get to the end of that purple group, we have filled all the electrons into that d orbital. It's completely full. So the first example would be zinc. 3d10 is zinc because it has 10 electrons, right? 2 in each one of these. Now, I hope you're starting to see a pattern with the periodic table. If we went to F's, right, we can't have F's with 3D. But if we had 4, we could do 4F, right? And that means we have a possibility of 3 for the L's. So we could have -3, -2, -1, 0, +1, +2, +3. That's 7. We could have 7 orbitals at this subshell. Right? So how many elements can we build? 14. So if you look at the lanthanides and the actinides, count the squares, there are 14 squares there. You can build 14 elements with F orbitals. And that's what we do for the lanthanides and the actinides. Okay, let's see. All right, so how do we know the order of energy for the orbitals? Well, this is a method. It doesn't explain based on the quantum mechanical model. This method doesn't explain how they arrived at this or why it is this way. This is just a method for ordering for the Aufbau principle. So if we have the principal quantum numbers on the left, and then next to them are the available subshells, then the first one is 1s. That's as far as you can go. Can't go any higher. 2s can also have a 2p. 3s can have a 3p and a 3d. And 4s can have a 4p, a 4d, and a 4f. And then 5s can have a 5p, 5d, 5f. It can actually have a 5g, but we don't need g's. All right, there are not enough elements, discovered elements, to accommodate the g's. So I stopped at F. And then we can go 6s, 6p, 6d. And the reason I'm stopping there is because of the way we're going to chop this up. So we have 7s and 7p, and that should be enough. So you go diagonal like this, right? And then when you get that one full, you go around here, you go around here, and you take this diagonal. And then you go around here and take that one, right? So far, we're in numerical order and letter order. 1s, 2s, 2p, 3s. Then we start up here, and we go down like this, right? 3p to 4s, right? We're still in logical order. But now, instead of going from 4s to 4p, we have to go back and pick up 3d. Then 4p and 5s. Like that. Okay. So this is an expression of how the energy increases for orbitals in the quantum mechanical model. So as we get to 4s, the 3ds are actually, let's see, 4s. 4s is a lower energy than the 3ds because of its penetration effect, right? It has those 3 humps. One of those humps goes in lower than the 3ds, so it has to come first. Then the 3ds, the 4ps, the 5s's, and I think the explanation for this out of sequence is penetration effect. Okay. Oh, and on the right, how many electrons can be accommodated with these? Well, this one can have 2, right? Up and down. This can be up and down 3 times. So this one can have 8. And this one, since we have 10 more, we have 10 plus 8 is 18. And this one can have 14. So 14 plus, let's see, 2, 8, 18, and 14 is 32. And we can go on from there. Okay, so that's one way to do it. The other way, which I think is easier, is to remember how the periodic table is structured. Right? So let's do some of these and use the periodic table to build their electronic structures. So if we start with sulfur, right? Sulfur has 16 protons, 16 electrons in the neutral atom. So 1s2, right? Got that period. Go to the next period. 2s2, right here. And we go across here, 2p. Go all the way across, 6. 1, 2, 3, 4, 5, 6. Then we come back to 3s. 2. And then we go to 3p. Let's see how many we've got. 2, 4, 10, 12. That leaves 4 more, right? We can put all of them in that 3p. Okay. Now, does that make sense? Yeah. Remember, oxygen had 4 in its p orbital, only it was 2p. Sulfur is just below oxygen in the same group, so it has 4 in its p orbital. It's valence p orbital. That's what it looks like. Now that's the, what do we call that, shorthand or abbreviated. But we can further abbreviate this by noticing that as we built this, we passed through neon to get to the next ones. Okay? So if we take these right here and we say those are neon, and then we can put that in brackets and say what's left over are the valence shells. So we can pull out the valence shell and then put everything else into a noble gas core. These are core electrons. These are valence electrons. And that would be another way of expressing the electronic configuration for any of the elements. Now, if on homework or test, the question is, give me the electronic configuration, the complete electronic configuration. Let's do it this way. If you're allowed to do the abbreviated, then you can do it that way. Let's look at barium. Barium is a whole lot bigger. So we can, I think we're going to use the abbreviated version for barium. Because barium is so big, right? It's down there, it's got 56. Okay, so let's back up. Barium backs up to xenon. So the core is like xenon. Excuse me. Let's do this and put 54 in here. So what's beyond xenon? We're down to the 6th period, s orbitals. 6s2. 2 plus 54 is 56. So that's the abbreviated version for barium. I think I got, yeah, we did it abbreviated there. Europium is ridiculous. Europium is lanthanide. And well, just for kicks, I'm not going to have you do one out of the lanthanides and the actinides because they're just too complicated. But this is what it would look like. Europium is 63, right? So if we went back to europium. Now, where does this insert in the periodic table? Notice 58 goes right in here, right? So we've already come from xenon 54. Where did we have to go? We went through 6s2. And then we dropped down here and went to 5. Notice that this period is 4s, 3d, then 4p. So the d's drop down 1 level for each period. F's dropped down 2 levels. So if this lanthanide was in the 6th, this is going to be 4F. So 4F, how many are left over? Well, let's see, we had 56. Was that 7? 1, 2, 3, 4, 5, no, 6. Oh, 7. Lanthanum, I forgot lanthanum. So lanthanum and D. I think lanthanum is a D, so that would be 5D1. Well, this is what we would expect it to be. And then 4F6. Okay, here's the problem. Electrons want to be in the lowest possible energy state that they can. And in this arrangement, they like to have either half-filled or whole-filled D and F orbitals. So a half-filled D would be 5. A half-filled F would be 7. This close to a 7, what happens is, I think, it steals that one, and the D orbital is now empty. Now let's see if that's true. Let me see if I got it right. Yep. So that's what we call an anomaly. It doesn't fit the pattern that we would normally expect. And we're going to see some of those in the D's. I'm not going to throw the F's at you anymore, but I do want you to understand it in terms of the D's. So we'll come back to the D's in just a minute. All right. Now that we know how the periodic table is structured, we want to describe some trends. Of measured parameters. Ionization energy is the first one we're going to look at. Second one is electron affinity. Third one is atomic radius. So first of all, how do we define ionization energy? We want to know how much energy does it take to remove one electron from a neutral atom. Okay, the trick is you want to be sure that the energy you're measuring is the actual energy required to promote that electron to infinity. In other words, make it leave the atom. And in order to do that, you can't have any other forces that are being overcome. So if your element happens to be a metal, you got to melt it and then vaporize it. You have to put enough energy in there to make it a gas, because once it reaches a gas and it's an individual atom, then you can remove an electron, and you know the energy going into that process is the one that you want measured. Whereas you don't want to measure the phase transitions also. That muddies the water. Right? So that's why we write it this way. Ionization energy is written this way. You have the element, and it must be a single atom gas. So just because it's a gas doesn't mean it's eligible for ionization energy determination. Suppose you have a diatomic gas, like hydrogen, oxygen, or nitrogen, or fluorine, chlorine, bromine, iodine. Well, chlorine and iodine are a different subject. But if it's already a gas and it's diatomic, you got to break that bond between the two atoms. And it's got to be a monatomic gas. Then when you add energy to it, you'll get a positive ion in a gaseous state, plus that free electron. That's how we express ionization energy. And the amount of energy going into it is that ionization energy. And that's the first ionization energy, where you remove one electron. Now we can go to the next step, and if they're a polyelectronic atom, we can remove another one and figure out how much energy it takes. And that's what we've done in this example. Magnesium as a gas, and just put a G next to everything in there. Those are all gases. The ionization energy for 1 mole of magnesium gas atoms is 735 kilojoules. Right? And it's going to be a positive number because, remember, for systems, when you add something to them, it's a positive value. When you take it away from the system, it's a negative value. So we add energy to go from here to here. So this is always going to be a positive value. Okay, so the second ionization energy, we're trying to remove the second electron. Notice that it takes more energy, right? And that's logical because you're trying to remove a negative electron from an already positive ion. Right? So it's pulling on that electron a little harder. So we have to add more energy, about twice as much energy to get the second one out. Okay, and remember, magnesium, for our example, let's say magnesium is 12. So we have 1s1, 2s2, 2s2, and that's then we 8. So it's 2p6 and 3s2. So that's 10, 12. Okay. So where's the first electron coming from? Right here, the highest energy. So if we remove 1 electron from that one, that gives us a positive charge. If we remove the second electron, then we no longer have need of that one, and we have a 2+ charge. So do we have any more valence electrons in there? Nope. The rest are core. Right? And this would be the electronic configuration of neon. The noble gases, remember, the noble gases don't react because they have completed shells. So this is considered the core, and in order to get an electron away from that one, it's going to take a massive amount of energy. That's why you see the big jump from 1400 to 7,000 kilojoules. Because when you try to remove a core electron, it takes a whole lot more energy. Not just because it's 2 positives, but because you're removing it from a stable noble gas configuration. Okay. And that trend is characteristic of all elements. Once you get to the core, then the amount of energy required jumps way up. Okay, that's ionization energy. Now, what is the trend in the periodic table? The trend for ionization energy is it increases from left to right. And this is first ionization energy. Right. If we speak of second ionization energy, then it depends because second ionization energy for the alkali metals is going to be massive. Right. So that's not a fair comparison. We're only talking about first ionization energies here. And why does it increase from left to right? It's something known as the effective nuclear charge. You're increasing the number of protons in the nucleus. And that provides a stronger positive charge to hold on those electrons. And the electrons are coming from the same orbitals. So they're not really significant. There's not really a significant difference in the energies of these electrons. They're in a narrow range for the second period in this case. Right. So the adding protons is effectively holding on to those electrons much stronger. Right. So how about what if we go down in a group? Right. That's decreasing. Ionization energy. Let's see, I should put increasing here. Okay, why does the ionization energy decrease as we go down in a group? As you go down in the group, the valence electrons are at much higher energies already. They're in these outer orbitals, right? And the further you are away from the nucleus, the higher your energy state. So it takes less energy to kick a nuclear electron off of an outer orbital than it does a closer orbital. So as we're adding electrons in these periods, we're adding them to outer shells, and it takes less energy to go to kick an electron from here than it does from here. That's one way. The other thing that we're doing is, as we add electrons to these inner shells, these core shells, they are shielding the outer electrons from that positive charge that's in the nucleus, because we're adding more protons as we go down, quite a few. But we're also adding electrons in these lower core orbitals that are shielding the outer electrons from that positive charge. So for that reason, as you go down, you decrease the ionization energy. And obviously, if you go the other direction, you're increasing, right? So the trend for the whole table is lower left to upper right, we increase first ionization energy. Okay. I already mentioned that. Now it's in black and white. Okay. So I got a messy chart up there. I probably ought to do something about that. It's going to be kind of hard to erase things that I don't want. So maybe what I ought to do is just erase the whole thing. Start over. All right, this theory has gone way, way, way off the rails, so I'm gonna jump it and start over. Okay, so here's our periodic table. Minus the lanthanides and actinides. Let's see, come over here about like that, then go like this, like that. And there's our hydrogen, and there's our helium. This is 1, 2, 3. 1, 2, 3, yes, and then 4. Okay. If we look at the ionization energies for across the periods, right? We know that generally speaking, the ionization energy increases as you go from left to right. That's definitely a generality. But we know that the very highest ionization energy for each period is going to be the noble gases, because they're essentially core and they have no valence electrons. Well, technically, by definition, they do, but those valence electrons are held very tightly. So what we get is hydrogen gives us a certain value for its ionization energy, and then when we go to the noble gas, helium, it jumps way up. But then when we start a new period with lithium, it goes back down. And then we go up to, lithium, beryllium. Beryllium takes a little more energy, left to right. But when we go to boron, it drops back down again. And that's largely because we're now in p orbitals. And p orbitals in general for the second period, they're a little bit higher in energy. So it's going to take less energy to kick that electron off. And so it drops back down a little bit. And then as we trend across, we go boron, carbon, and then when we get to nitrogen, we see nitrogen to oxygen, we see an anomaly. So let's look at that one. And this trend is going to be, the trend from beryllium to boron is going from s orbitals to p orbitals. Going from magnesium to aluminum, similarly, s orbitals to p orbitals. But when you get to nitrogen to oxygen, nitrogen is, all right, nitrogen is 7, right? So it's going to be 1s2, 2s2, 2p3, okay? And then oxygen is 8. So it's going to be 1s2, 2s2, 2p4, okay? So we have 2 electrons here, 2 electrons there, and 3 here, like that, like that, like that. But for oxygen, we have 4 electrons in that p orbital, in those p orbitals. So we go like that, like that, like that. Hunt says now we can pair them. Okay, here's the difference between nitrogen and oxygen. These are all unpaired electrons. They're as far away as we can get them in the p orbitals. So the repulsive effect is similar to a trend across like that. Right? If we add electrons to this one, they're separated, so we get a nice clean increase in ionization energy. And we see that from, let's see, where's nitrogen? Here we go. From boron to carbon to nitrogen, we see that increase. But when we get to oxygen, now we have to pair these 2 up. And those 2 electrons are in the same orbital, opposite spins, but the same charge, they're repelling each other. So it takes less energy to kick that electron out because it's already being repelled by its neighbor. So that's why the oxygen drops down a little bit. And then we start going back up because now with oxygen, fluorine, and then neon would be full and it would jump way up. And you can show that same trend for phosphorus to sulfur. Right? Phosphorus would have actually a 3p, would be like that. And then sulfur would be a 3p like this. And you get that same effect, the repulsive effect that lowers the energy. That's one of the anomalies in this trend. Okay. Explain why the graph of ionization energies versus atomic numbers across a row is not linear. Largely due to electron repulsions. That's the major factor. And where are the exceptions? Well, between beryllium to boron and nitrogen to oxygen. We can look at it that way also. For repulsions, if we go from beryllium to boron, let's do that one real quick. I'm going to run out of time, so if you guys have to go, then you won't hurt my feelings. So in this case, beryllium is beryllium is 4. So we get, you know what? That's all beryllium has. I think my explanation is better than repulsion. As boron has 5, it goes 1s2, 2s2, 2p1. Yeah. This anomaly is due to difference in energy of orbitals, whereas the nitrogen to oxygen is due to electron repulsion only. Well, not only, but major factor. Yeah, this is the fact. This is a higher energy level. So when we add this one, it's going to take less energy to remove that than we would expect if we had another electron theoretically put into an s orbital. Okay. So I got 3 minutes to do the rest. Think I'm going to make it? Not likely. Which atom will require more energy to remove an electron and why? Right? If we look, as sodium is in the same period as chlorine, so from left to right, it's going to take more energy to remove an electron from chlorine than it is from sodium. Ionization increases from left to right. Okay. How about lithium and cesium? Let's see, lithium and cesium are both alkali metals in that same group. So it's going to be less energy for cesium and more for lithium. All right. Which has the larger second ionization energy? Okay, so lithium versus beryllium. Lithium versus beryllium. Lithium is 3, this is 4. Okay, so this is 1s2, 2s1, and this is 1s2 and 2s2. So we're looking at second ionization energy. So the first ionization energy would get rid of this one, right? And that would make it a positive ion. This one would just take 1 out of the S and make that a positive ion. Let's see, and that's the first ionization energy. How about the second ionization energy? Where's the electron coming from beryllium? It's coming from that s orbital, right? It's still valence. This is still taking a valence electron. So that one is going to be an increase in energy required. But if we try to take an electron from that core, this is going to be a massive second ionization energy. It's going to be much, much greater than this second, because the electron's coming from the core. So lithium would have a higher second ionization energy than beryllium. And this chart comes out of your book. It just shows the trends as we go across sodium, magnesium, aluminum, silicon, all the way across to argon. Notice that it takes more energy for each of the valence electrons to be removed. But once you get to the core, once you've used up all your valence electrons and you get to the core, then the amount of energy required just jumps up in massive amounts. Okay, that's on the other side of that stair-step line. The other trend you may notice is that for the core electron removal, as we go down from sodium to argon, as a step on the outside of that line, you find that the core electrons, the ionization energy for the core, it could be a second, third, fourth, fifth. You go down, it increases dramatically as you go down. And that's largely due to the fact that you're removing those core electrons from an increased nuclear charge as you go across the period. Okay, next trend. That was ionization energy. Next is electron affinity. Energy. The temptation here is to think of electron affinity as the inverse of ionization energy, but it's not. Because if it were, then the inverse would be the positive ion plus an electron yields a neutral atom, and that's not the way it works. Electron affinity, we start with the same gaseous element, and we say, how much energy do we get back if we allow one electron to be added to that and make a negative ion? So both of them start with the neutral. In ionization, we remove an electron. With affinity, we add an electron. And the value, electron affinity value, is always going to be negative, right? Because as we add the electron, it moves from this higher energy state to a valence shell, which is a lower energy state, and it gives up that energy. So since it gives up the energy, it leaves the system, it's a negative value. So the more negative the value, the more electron liking, or the higher the affinity for the electron. So what are the trends? All right. In general, as we go across a period from left to right, the electron affinity becomes more negative. So electron affinity, as we go this way, is more negative. That is, the electron affinity as we go to the right increases. In other words, a stronger pull on the electrons gives us a more negative value as we go from left to right. Okay. However, as we go down a groove, the electron affinity becomes more positive. So there's less attraction for the electron as you go down. The electron will be, if it's a negative value here, it becomes a smaller negative value as we go down. Okay. So the trend would be from lower left to upper right, like the ionization energy on this trend is more negative as you go from lower left to upper right. And for similar reasons. As we go from left to right, we're increasing the effective nuclear charge, which draws electrons in more strongly and gives up that energy. And as we go down, we're adding electrons to outer orbitals, which means you get less energy back as they attach to outer orbitals than you would if they attached to inner orbital. Okay, it's enough said about that one. We'll say more later. Atomic radius is kind of a operationally defined term. It's a little more difficult to get a handle on it. What we have to do is define what we mean by atomic radius, right? Because remember, you got this very dense nucleus, and then you got these electrons floating around here that are just kind of, well, they have very low mass. So it's a little difficult to find out where's the boundary of the atom. So that outer limit is the problem. We generally speak of two types of atomic radius. One is the metallic radius. So we have this solid metal, and we use X-ray diffraction techniques to find out how far apart are the atoms in the layer. We'll talk about that. I think it's in the second semester, about using X-ray diffraction to determine the distance between these stacked atoms in a metal, right? Maybe like that, say, or sometimes they're a little different. But the distance between there, we can shine X-rays at them and gather information from, and using forgot the name of the law. Using a calculation, we can find out the distance between the layers. So if we know the distance between the layers, then we take half of that distance between the nuclei, and that's the atomic radius. That's what that figure is trying to show us. The other possibility is called the covalent radius. And obviously, this is going to be discovered in covalent compounds. And there are a number of techniques that are used, and it takes a real seasoned lab tech to do this correctly. We're generally looking at homonuclear diatomic molecules, so we have to form diatomic molecules. Some of them are easier than others. Like the diatomics at room temperature, like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are very well behaved, but If you want the covalent radius for any other homonuclear, that is the same element in pairs, then you have to force them together. And it can be done. Once you do that, then you can measure with various techniques like X-ray. You can fire electrons at them. You can use neutron diffraction, microwave spectroscopy, and some others to determine what's the distance between those nuclei. And then you take half of that distance, and that's your atomic radius. That's the covalent radius. Okay, so if we can agree upon values, a general fit values for atomic radius, then we can look at trends. And the trend from left to right is the atomic radius decreases. Yeah. No. Yep. So left to right, the atomic radius decreases. And this is largely due to the fact that we have an increased nuclear charge. It's drawing on those electrons and shrinking the size of the atom. So fluorine is going to be a smaller atom than lithium. And chlorine will be a smaller atom than sodium. As we go down a group, the atomic radius tends to increase simply because we're adding electrons to outer shells. Higher energy levels makes the atom bigger. Plus, those poor electrons are shielding those outer electrons from nuclear charge. So they don't feel the pull as strong from on the outside, and they can kind of spread out more. All right, so the overall trend would be from lower left to upper right, the atomic radius would increase. And we find that the behavior of the representative elements, right, these first two and these last six, they're reasonably well behaved in terms of these trends. When you get into the transitions, then you sort of get into, you're sort of a roller coaster. So the atomic radius trend holds fairly well for the representative elements, but not so well for the transitions. So which would be the larger atom of these, sodium or chlorine? Sodium, right? Because as you go from left to right, you're shrinking. That would be the larger atom. Lithium and cesium. Now we're up and down in the group. Lithium would be the smaller, and cesium would be the larger. Okay. Now I'm going to throw you a curve here. We talk about larger versus smaller in terms of the comparison of hydrogen and lithium. So hydrogen is a 1s, a 1s1. And lithium is a 2s, is a 1s1 and a 2s1. 2. Okay. Which one is larger? Well, think about the number of protons. This one has 1 proton. This one has 3 protons. We're talking simply about the 1s orbital, excuse me. The 1s orbital, right? So the 1s orbital here is feeling the pull of 1 proton, whereas this 1s orbital is feeling the pull of 3 protons, and these are in the general same area, but with this many protons pulling on that orbital, this one is smaller. So hydrogen would be a larger 1s orbital. How about energy? Remember, higher energy is farther from the nucleus. Lower energy is close to the nucleus. Right? So the lower energy is going to be the 1s from the hydrogen. Excuse me. No, lower, closer to the nucleus. I'm sorry. This would be a larger orbital. This would be lower energy because it's pulled closer to the nucleus, which decreases its energy. Did I confuse anybody? I started to confuse myself and then I caught myself. Okay. Arrange these elements according to increasing ionization energy. So oxygen, fluorine, and sulfur. So oxygen is going to be right about here. Yeah, right about there is oxygen. Fluorine is going to be here. And sulfur is going to be here. So for first ionization energy is what they mean. Increasing ionization energy would be from sulfur to oxygen to fluorine, as it increases from lower left to upper right. Okay, how about atomic size? Well, we're going to increase atomic size, increasing atomic size from, wait a minute. I got this one wrong. I'm sorry. That's wrong. We're increasing this way, decreasing this way, increasing this way. So, apologies. Radius is increasing from upper right to lower left. Okay, so be sure and correct your notes on that one. So atomic size would be just the opposite. It would go back. So atomic size would be this way. Like that. So it'd be fluorine, oxygen, sulfur. Okay. Oh, final thoughts. Is that it? Yeah. Okay. Didn't go too far over, 15 minutes. It's the number and type of valence electrons that primarily determine the atom's chemistry. So that's why we see that the same number of valence electrons are in each group, and that determines their related chemistries. Electron configurations can be determined from the way the periodic table is organized. And if you practice it, this is a whole lot easier than trying to do that diagonal thing. Well, eventually you're going to memorize them anyway. And if you do enough of them, they're going to be second nature. Certain groups in the periodic table have special names. Yeah, we've talked about those. Basic division of the elements in the periodic table is into metals and nonmetals. Yep. Oh, that is final thoughts. Okay, so we finished introducing chapter 7. Okay, and now we've got a buffer scheduled for Tuesday. What we can do is use that buffer time to introduce molecular weight of an acid via titration. We can look at the lab in detail before we go in there. You still have to prepare your notebooks, but let's see. Are there any pre-lab questions? Yeah, we have discussion and pre-lab questions. We can look for those in that session. Okay, just have your notebook set up to receive the information.